Hello, welcome everyone to today's webinar. We are just going to wait for a few minutes so that everybody get in, and we'll get started. So, as a reminder, in this session, I'm going to cover how to use high integrity technologies from AdaCore to their fullest. Basically, I will give you a deeper dive into AdaCore latest software releases and things that are planning in our roadmap. I will also tell you how to leverage high integrity technologies such as Ada, Spark, C++, Rust to help you. I will show you how some of our customers have been using our technologies so that they manage to improve the way of work. And I will tell you what we plan in the future for everything that we are working on. Please note that this event is being recorded, so the link will be available to you via email after the webinar is finished. You won't be seen or heard, but if you are not comfortable with the recording, you can sign off. As I'll introduce myself. My name is Ruiz, and I'm one of the product managers at AdaCore. I am responsible for Gnat Pro, and more particularly for the embedded part of the technology. If you have any questions during the presentation, please use the tab that is at the bottom right of your interface. If you do that, our AdaCore team will answer your question in the Q&A chat. And if by any chance, if we run out of time, we will follow up with you later via email. Another thing is that before we begin, I'd like to get your feedback about any topics related to high integrity technologies that you would like AdaCore to cover in any future webinar or tech update. If you do, let us know. We will open in a moment a poll on your screen so that you can submit your responses there. Okay, so let's start with our agenda for today's webinar. I will start by presenting new platforms on which we have been working. These platforms relate to, for example, software frameworks, typically new OSs that we support, new hardware targets, new architectures that we support with our tooling, followed by new languages that we support, and new profiles that we support on these languages. We will then talk about cybersecurity and the different aspects that we at AdaCore deal with. We will talk about how we deal with cybersecurity within our products, cybersecurity for the code that you produce, for the communication protocols that you use, and even how to enhance your testing to improve security of your product. And at the end, we will talk about a couple of user stories that will let you know how you could use our technology in a better way. So let's start with software platforms. This is a short version of our roadmap for the last few years, including 2024. I'm not gonna bore you with all the details, but just letting you know that we tip, as usual, we follow upgrades into the different OSs that we support. You can see, for example, in 2024, we are going to support QNX 8.0, the latest released versions of VxWorks 7, both in kernel and RTP modes, and even to run on top of the hypervisor. We are supporting newer versions of Lynx OS. There is here a mention of bare metal Morello that we'll talk a bit about in later slides. So we keep improving, increasing the number of software targets that we support. Something new is that we are also supporting LLVM backend in our products. We have been, and we still are, of course, supporting the GCC backend for our products, but we want our customers to take advantage of things that are possible to do within the LLVM ecosystem. So we are increasingly adding new LLVM backends to our technology. One interesting use case of having two different backends for the same front-end Ada compiler, for example, is to use dissimilarity, meaning that for a given version of your software, you can compile it with the GCC backend and the LLVM backend, and you will get two different objects corresponding to the same source code that may help you prove that you are using two different images for the same software, and comparing the results, so that if in the event that one of the backends is generating wrong code, you can detect it with the other. So LLVM is not completely new within our tooling. We have been using LLVM for example, for our common code generator, the one that translates Ada into C. We have been using that for our Gnat for CUDA compiler. But this year, in 2024, we have introduced this backend for the x86 64-bit version of Linux, and we are planning to add new platforms with this backend. For example, Windows, bare metal ARM, bare metal Moreto, VxWorks, and some others. A relatively recent technology with which we are working and playing with is WebAssembly. WebAssembly is new technology that allows you to generate code that can be executed on many different platforms. These different platforms include web browsers, native and embedded platforms. And the idea is that you can get your code written in Ada, in Spark, so that you can ensure safety and security of your code. You compile, generate the WebAssembly, and that image can be run on different platforms, so that you take advantage of verifying the software once and run it on different targets. This is an interpreted language, so that we are working also on an embedded runtime, so that this WASM code can be interpreted, and this is being written in a Spark, so that you can prove the correctness of this runtime. Another software platform that we are experimenting with is FreeRTOS. FreeRTOS is a rather convenient target for when you want to develop something with a small footprint, but at the same time having access to several libraries and drivers provided for that platform. And what we plan and what we are working on is on providing you the capability of having ADA tasking, the restricted ADA tasking that is supported by the Jorvik profile on FreeRTOS. FreeRTOS is available on a range of different target hardware. Initially, we will focus on ARM targets, and we will probably include new ones depending on your needs. So now let's get into hardware, new hardware targets that we support. There is one that is very interesting, in my opinion, it's called Cherry, and the idea is that you take an existing processor, you take ARM, RISC-V, anything, and you extend it with some capabilities that are very interesting to enhance cyber security, because the main idea is that you are associating, for example, the pointers. You are associating not only the address to which it points, but also you associate to that pointer the memory area that is potentially available to this, so that you can ensure that you are not trying to access things that are not within the boundaries that are expected for you. Many of you have probably heard about the White House document talking about memory safety and how they want to improve the memory safety of the languages, the programming languages used. The idea here is that we are helping you, not only providing you with a language like Ada or Spark that is already memory safe, and that gives you a lot of benefits in terms of ensuring that there is no buffer overflow, you will never use a pointer after you have freed it. So this is given to you by the Ada language. We have a memory safe runtime when you are running Ada code that is ensuring all these capabilities, but we are enhancing this runtime so that we add to these pointers the information that is needed so that the hardware can check the boundaries of the things that you are accessing. And at the end, you have a processor that is able to check at execution time that you are respecting the things that you said. If a pointer, for example, if you declare a pointer to an array, this pointer will never be used to access outside this array. That will be detected at execution time, and an exception will be triggered. So this, as I said, this is an extension that is architecture neutral, but initially we are focusing on Morello. Morello is the ARM 62 version, 64-bit version of this Cherry architecture, and we are working on the Morello bare metal compiler and the Morello VxWorks compiler that is coming soon. So the idea, as I said, is you will have a memory protection at different levels so that if you are doing in your application things that try to, let's say, override the language rules, such as, for example, unchecked conversions, etc., you will have the hardware at the end that will be able to check that everything is correct. We talked about it very quickly. We have our Gnat Pro for CUDA compiler. The idea is to be able to, again, write your code in Ada, Spark, and split the code into the parts that are being executed in your host, and the parts that are going to execute on the NVIDIA GPUs that your computer has. For that, we have introduced the support for heterogeneous memory models. The idea is that CPU has its memory, GPUs have their memory, and we allow the means to very easily transfer data from one memory partition to the other. If you have a look at the code that is in the bottom left side, you can see that we define two different arrays, array pointers. The second one, the array device access, is a pointer to something that has specified a designated storage model. This this aspect is telling you that this pointer is pointing to the memory area that is allocated to the GPU. At the if you go a bit down, you can see the device complex computation that has an attribute with CUDA global, telling that this is code that is intended to be run on the CUDA platform, meaning the GPUs. And on the right hand side, you can see the pragma CUDA execute that is basically saying, I want you to execute this code on the GPUs. And at the end, the last statement is the hc.all equal dc.all is it's an example of how to transfer things, how to transfer the result that are stored into the GPU memory model into the memory of your host. So You write Ada code in a simple manner, and we provide you with the machinery, internal machinery to do the transfer between these two memory partitions. Languages and profiles. So if you are familiar with Ada, you probably know about the Ravenscar runtime that has been around for quite a few years already. The new Ada 2022 version includes a new profile which is called Jarvik, which is relatively similar to the Ravenscar profile. The idea of this profile is that it gives you a tasking model that is specially designed for safety and security critical applications that allows you to create tasks unprotected object statically at library level, not anywhere else. Gives you a preemptive fixed priority scheduling so that you can analyze the timing of your application. You ceiling priority protocol is enforced so that you bound any potential priority inversion. And if you compare Jorvik to Ravenscar, is basically removing some of the restrictions that were there, that were interesting in terms of timing analysis, but sometimes were a bit too restrictive, and they limited quite much the expressiveness of your application. So things that have been removed, there are a few things that have been changed in the field of protected objects. So now the entry queues have an unlimited length by default. You can use pragmas, you can use aspects to restrict the length if you wish. The expressions that you use on barriers are a bit more complex now. You can use some more expressive power to express these barriers. You can use in terms of timing, you can use the calendar package, and you can use relative delays, not only absolute delays like in Ravenscar. And there is a new concept that was added to the language and didn't exist at the time of the definition of the Ravenscar profile, which is the synchronous barriers that you can use with the Jorvik profile. So at the end, what you have is a platform intended for safety and certifiability, because you can do timing analysis of your final application. You can very easily analyze memory usage of your application. There is no need for dynamic memory. Everything can be static. You can use dynamic memory if you want, but you can already use this profile without any usage of dynamic memory. And underneath your application, you have a very efficient and streamlined runtime that is relatively easy to certify, because its size is quite reduced compared to the full Ada runtime. Okay, C++. We have introduced in our offering the support for C++ on bare metal platforms. The idea is to provide you with a certifiable C++ runtime that you can use on a very wide range of bare metal targets. For example, the list that we support at least today is ARM64, Leon 3 for space, PowerPC, RISC-V, Intel x86 64-bit. This is the range of targets that we support today. What we support is what is called the freestanding profile of C++. This is a profile that was defined for targets without any operating system, and it allows you to do already many things. For example, without even needing any runtime support, any runtime library, you can have access to quite a lot of the basic core C++ features, such obviously polymorphism, dynamic dispatching, constructors, destructors, templates. All that is available without even needing a runtime underneath. We also provide a streamlined C++ runtime that is compliant with the freestanding profile that I mentioned, and that is being used if you need to use some more complex C++ features, such as, for example, runtime type information. If you need to query that kind of information at runtime, you need some library support. Exception handling comes with some needs in terms of runtime, dynamic memory, etc. But even with no or very reduced C++ runtime, you can do already quite a lot of C++. You can use a lot of the aspects of C++ to make it interesting. Rust is another language that we are supporting. So, in terms of what we support, what is included into the bundle of the Rust tooling, basically you have obviously the Rust compiler, the cargo, which is the tool provided by Rust to build and manage all your packages. We provide you with a debugger, and of course a set of libraries that allow you to use Rust. We typically include 4 different runtime libraries: libcore, which is the foundation of the standard library; the standard library itself, which is supported on native targets. It is not included in bare metal targets. Liballoc for use when you use the heap, and libproc macro for the macros that you use in Rust. In terms of accessibility, what exists already and what is going to be available. So we already have wavefronts available for a few targets. For example, x86 64-bit Linux native. We have bare metal ARM 64-bit, as I said, without the standard library, and Linux, but targeting ARM 64 bits. That is what we have today. But new things are happening. New things are coming. For example, the Windows version is about to happen, and VxWorks in both RTP and kernel mode will happen this year. And obviously, if you need any other target, just let us know and we can discuss that with you. Ada language. So we are working on many, as you will see, many different kinds of enhancements to and extensions to the Ada language. They are controlled with compiler switches, so that if you don't use them, if you don't use these switches, all these new capabilities are not available, and the compiler will tell you that you are trying to use something that is not supported. But the Gnat X mode will give you access to a set of pretty well tested and stable capabilities that you could use in your projects, and we will see a few examples of them. For those wanting to test bleeding edge things, for example, to give us feedback about how good it is, how interesting it is for them, there is the Gnat X0 flag that allows you to a bigger set of features. But as I said, some of them are kind of experimental. So I wouldn't put these things into production system yet. So one of the things that we have added is kind of syntactic sugar, is the possibility of fixing the lower bound of an array. In Ada, you can have either fixed bounds or bounds that are undefined. Sometimes many people asked whether it would be possible to fix the lower bound, because it can be pretty convenient sometimes, and it matches a bit the philosophy in other programming languages. So one of the possibilities that you have now is to fix the starting index of an array while leaving the end undefined, as you can see in this slide. Okay, another convenient feature is the possibility to provide defaults for generic formal functions. As you can see in this example, there sometimes you can define a generic template with subprograms that are by default, that you can provide a default that is useful and relatively simple, without forcing people to redefine the same default behavior every time. So you can see that in this example with the function copy. The function copy is already provided with a default implementation that you can obviously override. String interpolation is like you can see here. You can define, like in some other programming languages, you can define strings on which you can put variables and expressions to be interpreted while producing the string, so that you can use, for example, here the variable name in the middle of a string, and it will be interpreted with the value that contains that variable. And not only that, you can use expressions like x plus y to represent that you want to print the result of adding these two integer variables. What else is you can declare now local variables without being forced to declare a declare block. So this is this capabilities. This is new. Doesn't add any any new possibility, but it simplifies the way you write your code. It probably makes it easier to read. For examples like this, where you are defining a variable just to store the result of an operation, so that you can do that without being able to do the declare variable begin, end, etc. So it's basically for readability and to make variable declarations closer to the place where you use your variable. Case pattern matching. This is a way to provide you with more flexibility when you use case statements. So as you can see here, you can now define write when statements that are much more flexible than what exists in the language definition. For example, if you look at the when statements that are written down in this example, you can use expressions like when. So you have a case that relates to a record type, and within the when statement, you can access to the fields of this record statement, and use things like if field f1 is positive and field f2 is positive, then do something else in other cases. So it gives you much more freedom when you write your case statements. Case pattern matching is you can, as you can see in the case statement at the bottom, you have a when statement saying has value true, val, undefined. You can take this value within the record, and you have access, a very easy access to it within the return, or within the code that you write within the when statements. Again, this is a help that simplifies the way you write your code, and it is helpful in terms of readability of the code that you write. Conditional when constructs. You probably already know the Ada capability that allows you. For example, you have a loop, and you can write in the middle of the loop and exit when something. So you can exit the loop when a condition happens. The thing is that we thought that this conditional these conditions for control flow were quite useful, not only in loop statements, but in other cases. So we have extended the cases where you can use this kind of when constructs, such as, for example, return when condition. If you are within a procedure, you can, instead of writing if condition then return, you can simplify the way you write that, saying return when condition. In a function, you can say return true when another condition. Exception handling can be written in a more compact way, in a similar way, so you can raise an exception when a condition happens. So again, much more flexibility in the way you write your code that will very likely help you with the readability of your code. Things that are not there yet, but on which we are working for Ada. One of them is the possibility to put a boundary on the size of a class for tag types. What's the idea? The idea is basically that you declare the root of a tag type, and you fix the maximum amount or the maximum size for this tag type and any of its descendant. The advantage of that is being able to easily create, for example, an array of objects of this class. These objects, as you can see in the last line of the code that is shown here, you can declare an array with objects that belong to the class hierarchy, but they can be of different actual types, different actual tag types, and that is possible because we are bounding the size of this hierarchy of types, so that we can declare in an array with the maximum amount of size for each of the elements. Something that you cannot do if the maximum size of the elements is unknown. So typically you would need to declare an array of pointers. With this capability, you can create an array with the actual objects within the array. Same thing, same concept, but for arrays. You can use, as you can see in the third line of the code that I show, the aspect with definite. And the idea is that you are going to bound the size of the array, and you can the actual object, the actual elements, the number of actual elements within the array can change and can evolve. As you can see in the code, you can define an array that has 4 elements. You can copy on top of it an array that has 2 elements. You can add 2 new elements to this array. All that works, provided that you don't exceed the maximum capacity that you define for that array. As you can see in the last line, where you try to allocate to A, that is a maximum size of 8, something that has more than 8 elements. So that is something that will fail. External initialization is capability that allows you to, when you have the initialization of an object is very lengthy. In this example, we are defining, for example, an array, a large array, a potentially large array of elements. If you put the values, if you enumerate the values one after the other in your initialization, it can be pretty lengthy and pretty unreadable. So one of the things is that you can define these initial values of objects within a separate file, and the compiler will allow you to use this file to fulfill the initialization of the objects. There is quite some work going on in the field of object oriented, with things such as, for example, we will see that fast controlling parameter, so that the equivalent to the this in C++ will happen can only happen in the fast parameter. We will see an example. The notion of constructors and destructors, and the notion of super to get to your parent in an easier way. We will see a few examples of it here. For example, for the first controlling parameter, the idea is to simplify the model, and basically it helps a lot when you return type. Sometimes the rules of that made the code a bit tricky. So now you can add an attribute to a type that is fast controlling parameter, meaning that it will control dispatching only if it happens in the first parameter of the subprogram. For example, here, if you look at the function child, there is the self t that is controlling, but there is another return t that, as the tag type t has been marked as fast controlling parameter, this return type is not controlling, doesn't have an influence in the dispatching rules for calling it. Another example is that in the function bar that you can see at the bottom, a parameter of type t happens in the second place of the parameter list, so it makes this function not a primitive method of the tag type t. So these are the effects of marking a type as fast controlling parameter. Constructors and destructors for people familiar with C++, that will ring a bell. The main idea is to make people with a background object-oriented in C++ having an easier migration path into Ada, so that when they are used to write C++ code, if they need to migrate to Ada, it is not a huge jump in terms of things that they can write. So these are the means to introduce this notion of constructors and destructors in a similar way in Ada. Okay, one thing that for example is a bit it goes in the same line as facilitating migration from C++ to Ada is getting the syntax closer to what people are familiar with in C++. And this is the case of this example. You can declare a tag type without saying tag type, but saying class, which is a notion that is more widely known. And this way, you can, for example, declare a class, declare subprograms that belong to this class within the scope of the class, and you can define private fields to the class. That looks very much similar to the way you would write a C++ class. Okay, so this is a subset. There are more things coming up in the Ada field, but this is I wanted to show you a few examples of them. Obviously, Spark is a language that keeps evolving. We keep adding new things. For example, one of the missing things in Spark was the support for abnormal termination, typically exceptions. How to introduce the notion of exceptions within the Spark analysis. So we have added a few things, such as conditional termination. You can add attributes to subprograms, saying whether that subprogram must terminate. There is no way that there is an abnormal termination in the middle of that subprogram. There is attributes like if you say if you set the always terminates to false, it means that it may be the case that that subprogram doesn't terminate. Or even you can be a bit more precise to help in the analysis, saying that it terminates when a condition is true. So you can conditionalize the fact whether you know whether it will terminate or not. And for the way to propagate exceptions from the bottom up in the call chain, you can add attributes like might propagate, meaning that it can propagate in some cases. You can define the notion that it can propagate the exception if a certain condition is true. It will for sure propagate an exception if some conditions are given, etc. So it gives you the expressive power to define what is the expected behavior of the different pieces of your application. In terms of usability, user experience of Spark, there is quite some work behind it. We have introduced what we call explain code, meaning that you use Gnat proof to prove your code, and if there is a problem, you will have an error message with a code. That code you can ask for more information about what that means, and this is what it explained in the first block of code. On the second, we have worked quite a lot in the production of counterexamples for floating point values. So now you can get, for example, in this case, you can have the possibility of an overflow in an operation. Gnat proof will give you a counterexample saying, for example, if you use A with this value and B with this value, this case will produce a float overflow. And on top of that, there has been quite a lot of work within the Spark team, focusing on improving the insurance and reliability of the tool. Cybersecurity. So as I mentioned, we are very much interested in helping our customers with cybersecurity. We typically approach this problem in two aspects. There is the security of our products and the security of the application that you write. In terms of our tooling, what do? We provide with what we call software composition analysis, which is basically a word to tell you all the software that we provide you, including any third-party dependencies, including licenses of the different pieces, and an analysis of the vulnerabilities that are known for these pieces of code. The way it works is that we are very much open to anyone reporting us vulnerabilities that they may find. We publish these vulnerabilities that are known to us within a shared database and within our website. I will show you how it looks like. We work when you download our tooling. We provide you with a software bill of materials saying, okay, this is all the things that are contained within this tool. And obviously, in addition to publishing vulnerabilities, we fix them, and we fix them in several different ways. For example, for our enterprise customers, these problems are fixed in wavefronts and all subsequent new releases. For assurance customers having the assurance Gnat Pro, the fixes will be available again in wavefronts and new releases, of course, but we can make them available in the sustained branches that they are subscribed to. And the way these advisories look like is like that. We have a web page where you can see the vulnerabilities that are known to us. So this is the part about our products. What do we do? Where are we active in terms of checking the contents of the tools that we provide to you? We work on another aspect is how we can help you develop code that is less vulnerable to attacks. Our aim is to help you prevent things like data leakage, fault injection, and any kind of memory-related attack that you can be victim of. So typically we have developed three main techniques to help you find these potential vulnerabilities that I will show you. The first one is the scrubbing of stack and registers. What that means is that if you use certain switches, Gnat can help you into cleaning or zero out the contents of the registers that have been used when you return from a subprogram. So you call a subprogram, you work on it, you use registers to do your computation. When you return, in order to prevent any potential leakage of data within these registers. So when we return, we will zero out them so that this information that has been used locally is not available to the upper frame. Same thing with the stack. When you collapse a program, you are using the stack for doing your computation. Before returning, we are cleaning up this stack space so that if the caller tries to read this piece of a stack, it will only find zeros. So no information can be leaked through that way. To protect against the control flow attack, we have implemented something that is called hardened conditionals, and the idea is basically to double check. You have code that looks like if condition, then do A, else then do B. So there is a first check of the condition in the if. So if the condition is true, then go to A. We add something else, that is when you go to A, instead of going straight to A, you will go to another part that is checking again, saying that, okay, if condition is true, then I do A, but if not, then I will abort because there is something that went wrong within this call. If I am here, it is because the condition should be true. If the condition is not true, is that something happened. So this is the kind of double check that enhance the security of the code that is generated for your application. In a similar way, we implement what we call control flow redundancy, that is based on instrumenting the code so that you add some tags in basic blocks, saying, for example, if you have a block of code that should be executed sequentially, you mark that you are in this block at the beginning, and at the end you check whether that tag, that node was added. If not, it means that you reached this point of the execution of your code in a non-expected way, so that you can stop because you know that something went wrong when executing this piece of code. Another way to help you is with the communication protocols that you use. So we have a product which is called record flags that allows you to do several things. First, so you define your protocol within the tool, and then the parser of the messages can guarantee that anything that you receive complies with the specification. The tool record flags will create the serializers to send and receive the messages in a proven way, because everything is generated using Spark. So both the parsers, serializers, and the state machines are written in Spark, so that you can prove the correct behavior of the different parts. And yeah, so you have a state machine that implements the communication protocol, but that you can check, you can verify to ensure the correctness of the implementation of everything. I mentioned that there is also a possibility to increase cybersecurity. There is a possibility that we can help you when testing your code. And this is with Gnat Fuzz, with this fuzzing technology that basically helps you detect unexpected vulnerabilities. The idea is that you take your code, and the fuzzing machinery is going to try to test uh, your code in a very exhaustive way. We check whether any parameters end up in, for example, exceptions or assertions that are not respected. So this is a way to increase the extent of your testing, trying to look for unexpected input data that causes the program to behave in an unexpected way. Okay, and finally, I have talked about many things that we are implementing, but one important thing is why we are doing that. So I have a couple of use cases that illustrate what they do, and how all the tools that I have been mentioning help them into the day-to-day business. So the first case is related to NVIDIA. You probably all know about NVIDIA, and what they came to us saying that they wanted to improve the safety and the correctness of the firmware that they provide with their GPUs. So they went from an implementation in C to an implementation using Ada and Spark for the code that implements this firmware in in an environment where they use part of it is using our bare metal compiler, is running on top of NoOS, and there is another part of it that is running on top of an real-time operating system. In addition to that, they used record flags to implement a security protocol and data model that they have, and they did it within the context of the automotive ISO 26262 standard. So the use of Spark is helping them raising the safety and the correctness of their firmware. Another case study, this time in space technology, is Latitude, that used Ada and Spark again for the software that they implement for a light launcher. And their feedback that we got from them is that the use of Ada Spark, because they started considering whether it would be useful or not. So the feedback when using Ada and Spark is that first, it reduced the life cycle cost. They consider that it helped them implement their code faster. And In addition to that, they got very good performances because they needed to use tasking, and they took advantage of the Ravens corridor tasking that, as I mentioned, is a very streamlined, fast implementation of multitasking in Ada. So they were very happy, and they were using our mentorship support to go with them and help them in the different phases of their project. Okay, so this is the end of the presentation. Thank you, everyone, for listening. If we didn't manage to answer the questions that you asked, we will follow up with an email with the answers. As I said, for everyone who signed up for today's session, you will receive a recording of the event in a follow-up email. So so you can have a look at the recording. You will have also a copy of the slides. If you look at the bottom right apps tab, and if you ask for or submitted any topic on our poll, we will take note of your responses, and we will try to make it happen in a future webinar or tech days. So thank you again to everyone for coming, and I hope you will have a great day.